Welcome to Chatterjee Academy. So today's session is on atomic structure, and I'll take the session for Bohr model. Okay, Bohr quantization conditions. So before going to Bohr model, I'll just give you a brief about the previous research. So initially, we discovered the atomic subatomic particle like electron, proton, and neutron. So you know that the role of the Rutherford alpha particle scattering experiment. Before that, there was a Thomson model. So Thomson told that electrons and protons are randomly distributed inside the atom. Then Rutherford did the alpha particle experiment, and we came to know that most of the part of the atom is vacant. The inside the nucleus, that's very small part considering the whole volume of the atom, right? The small part containing the neutron and proton. Okay, and electrons are revolving in different orbits. So, so most of the atomic space is vacant. So this was the Rutherford model. Then we have some limitation on Rutherford model, that's electrons is going to radiate energy and they're supposed to come towards the nucleus, because the charged particle is radiating energy, right? And they are supposed to because there is a force of attraction between the electron and the proton, Coulombic force of attraction, electrostatic force, and it is trying to get the electron toward the nucleus. And so this is balanced by the centripetal force, right? The circular motion. So if electron is going to radiate the losing the energy, it will not able to maintain the circular orbit. This was the limitation of Rutherford. Then came the Niels Bohr. So Niels Bohr solved this problem. He told that electrons will be moving in a stationary orbit. The orbit from where electron is not going to radiate energy, not going to lose energy. Okay, so it will be in a fixed energy state called stationary orbit. That means the word quantization came here. Like electron is not going to rotate, is not going to circle in any unspecified orbit. The orbit should be highly specified, and that has been the postulates came from Niels Bohr. And before Niels Bohr, there is a famous de Broglie hypothesis, wave particle duality, and that also helps here. So de Broglie, he did a famous discovery. He told that subatomic particle like electron, proton, when there is motion, they are having the wave nature. So they are having the material, the matter, and the wave, the radiation energy, right? So wave particle duality. So electron is having the both particle and wave nature. That's why, so de Broglie famous hypothesis is wavelength of that electron is h by p or h by mv. So h is the Planck constant and p is the momentum. So relation between momentum of that electron and the wavelength of the electron is bridged by the Planck constant. So lambda is equal to h by p. This is the famous discovery of the de Broglie hypothesis, right? So de Broglie specified few specified wavelengths for the electrons. Okay, so that's a relation, like lambda is equal to h by mv. Fine. Now Niels Bohr told four postulates, right? So those postulates are like that is the quantum condition. First, he agreed with the Rutherford model that yes, nucleus is in the center of the atom. That's fine. Now, for electron, there are three key words: quantum condition, stationary orbit. So, quantum condition means that n the orbits are specified. So, the condition is that angular momentum L is equal to nh by 2 pi, right? So, angular momentum of electrons, okay, which is L, that means mvr. M is the mass of the electron, v is the velocity of the electron, r is the radius of that electron orbit. Okay. Now n is the orbital number and h is the Planck constant. So this is the relation, like L is equal to mvr by okay, let me zoom it. Okay, fine. So okay, I think it's clear to you. So this L is equal to mvr is equal to nh by 2 pi. So this is the quantum condition, the quantized relations, right? So n is the principal quantum number. N is the principal quantum number. Now Next is the stationary orbit. So these orbits are stationary, right? The energies are fixed on that orbit. Next is the frequency condition. Now, whenever these electrons are jumping from the, electrons, when they are coming from high energy state to lower energy state, they are going to release energy, and when electrons is jump from lower to higher, they are going to receive energy. So energy absorb or energy emit, right? This will be, conditioned through this particular. Okay, so let me, highlight that part now. 1 minute. Okay, so we are now discussing about the Bohr model, Bohr quantization conditions. Before that, I have explained you the de Broglie wavelength. Okay, now the de Broglie told the dual nature of light. Okay, now Bohr told that the famous relation. Let me write it one more time. MVR is equal to NH by 2 pi. MVR is equal to NH by 2 pi. So this is mass of electron, velocity of electron, radius of the electron orbit. N is the principal quantum number. So this will define the orbit number. N is equal to 1, 2, whatever, right? So these are specified orbits for electron rotation. H is the Planck constant. Okay. So this is about the Bohr quantum conditions. Bohr quantum condition, right? Now, so n is the principal quantum number now, and stationary orbit. Now let me show you what about the stationary orbit means. The orbits are specified. Energy is the fixed energy orbit. Energy is not going to release from those orbits. Okay. Now let me show you about the frequency condition. So let's say this is the nucleus of the atom, and these are different orbits. So if electrons is, this is the, let's say, E2 and this is E1. So what happened that this is the high energy state and this is the low energy state. So electrons will jump from here to here. That time, okay, a photon will release, right? So that is the h nu. H nu is equal to E2 minus E1. Okay. So these are called the frequency condition. This is called the frequency condition, right? So that electrons will, release energy, or in a particular, energy packet, right? Electrons is going to release, or electrons is going to absorb. So electron will release energy when it will jump from higher state to lower orbital state. And next is when if electrons are in the E1 lower state, let's say we are, it's receiving energy, then it will jump to the higher energy state. This is also happen. So this is the frequency condition, and for this case they need to obey this equation. H nu is equal to E2 minus E1. So this jumping or emission or absorption electrons, that's highly specified. That are highly specified. Okay. Now I'll show you the energy calculation. Okay. Energy of the, let me zoom it again. One more time. Okay. Perfect. Now, okay. So I will show you the how to calculate the energy of the electron. Okay. So for atom, let's say, let us take a simple example of the atom. So there is the, let's say, atomic number is Z. So number of proton is Zp. So Zp positive charge here, and let's say one electron is moving, okay, of charge negative, and this is the radius, right? So electrons are in the circular path. So what is going to happen, that the centripetal force of the, for this circular motion will be provided by the electrostatic force of attraction, right? So that is, the force of attraction F is equal to, that K Q1 Q2 by R square. So here it will be F is equal to K, then it will be ZE, then it will be E, right, and R square. It will be R square. So this is about the Coulombic force of attraction for this one, right? These are the Coulombic force of attraction. Now this will be, this will be balanced by the centripetal force. So that means mv square by r is equal to k z square by r square. Okay, so this is the very important relations. Okay, that for electron to be in orbit, so it needs a centripetal force, and that centripetal force will be provided by this Coulombic force of attraction, and this equation is very important, right? From here we are starting, we are calculating the energy of the electron, right? So let's go for that part now one more time. So here what we are getting, like, mv square by r is equal to k z square by r square. Mv square by k z square by r square, right? Or you can write, from here what happened, that mv square is equal to mv square r, right? Mv square r is equal to k z square, or r is equal to k z square by mv square. R is equal to kz square by mv square, right? So this is one equation. We receive the radius of the, the radius of the electrons, radius of the electron. This is the equation for the radius of the electron. Now we will go with the Bohr model, right? So Bohr told that L is equal to mvr is equal to nh by 2 pi, nh by 2 pi, right? From here we are receiving that r is equal to nh by 2 pi mv, nh by 2 pi mv, right? So we are receiving this r from here. Now what we are going to do, we will just equalize these two parts, and from here we will receive the velocity of the electron. So this is equation 1, this is equation 2. We receive two equations, right? Now we will equalize these two equations to get the velocity of the electron, right? So what we are going to do, we are going to do so nh by 2 pi mv is equal to this. Okay, so velocity of the electron will be, so it will be vnh is equal to 2 pi m k z square, or v is equal to 2 pi m k z square, by nh, right? So this is the velocity of the electron. So you got the equation for the velocity of the electron. Okay, now we'll replace this velocity in r. So we'll got a more clear equation for the radius, right? So what was the radius? You already received. The equation of radius was r is equal to nh by 2 pi mv. R was nh by 2 pi mv. Now I'll replace this velocity here. So it will be nh by 2 pi m. Inverse of velocity is nh, okay, by 2 pi m k z square, mkz square, right? So now we have got a modified relation for the equation for the radius. So r is equal to n square a square, then 4 pi square, right? It will be 4, it will be 4 pi square, 4 pi square, okay. So this is the radius of the electron. So you got this equation. These are the famous equation, and these things are coming in your exams also, right? Now from here, if you want to calculate the the radius of the hydrogen atom, electron in the hydrogen atom, so what we are going to receive from here, okay? So there you have to keep z is equal to 1, and so z, if you put z is equal to 1 and n is equal to 1, because hydrogen is only single orbit for electron, you will get the radius of the electron in the hydrogen atom, right? This way you can calculate. So, and also the last part I will be showing you the speed of electron we got and the energy of the electron. In my next session, I will show you the spectral series of hydrogen atoms. But this is the base. This relation is the base. Rest others are built on this part only, right? Okay. So we have got the equation. We derive the radius of the electron, okay, and the velocity of the electron. Fine. Now we will calculate the total energy of the electron. So total energy means always what we are referring. Energy of electron. Energy of electron is the kinetic energy and the potential energy. So kinetic energy is half m v square, half m v square, right? So kinetic energy you already know that. So that will be k z square by 2r. So this is the kinetic energy. Why? Because we are just using this previous relation mv square by r is equal to kz square by r square. Okay. Using this relation, we got the kinetic energy equation. Now next is the potential energy. So potential energy, will be k q1 q2 by r. So here, so q1 is the jd, q2 is electron, r will be there. So it will be minus kz square by r. So this is the potential energy of the electron and this is the kinetic energy of the electron. Now total energy will be addition of these two parts. So total energy E will be k z square by 2r minus this one kz square by r. So now we got total energy is equal to minus k z square by 2r. Okay. Now we are just going to replace the value of r here. So we will get the total energy equation of electron. So that will be total energy will be minus 2 pi square m k square z square e to the power 4 divided by n square a square, right? So this is become the total energy of an electron. Okay. Now an interesting part is coming, like from this equation, if you see, most of the part are constant. So it will be like minus 2 pi square m k square z square e to the power 4 by a square. So this is a constant part and by 1 by n square. So En proportional to 1 by n square. So energy of an electron in an orbit is proportional to the 1 by n square. N is the principal quantum number and this is the constant part. This called the Rydberg constant or Rydberg formula, right? So this part is the Rydberg formula R. So now what is the general formula? We can like E is equal to R by n square. En is equal to R by n square, right? This is the energy equation of an electron. In the next class, I will show you the spectral energy of the different hydrogen atoms, spectral of hydrogen atoms, like Balmer series, Passon series, how those are coming. So this is the base relation. Okay. So okay, just go through it and practice like this. You need to practice it, so that you will be more confident. You don't have to remember this equation, right? So go this way. So how to calculate, I have shown you. Just practice 2 or 3 times. It will help you to memorize. You don't have to just copy the formula in your mind. Okay, that's a trivial. Just do 2-3 times practice. It will be helpful. Okay, thank you. Just keep watching my session. I'll have few more session on atomic structures. Okay, so just go through, and this will also help you the student of class 12, mainly for ICSE, CBSE, for those having the in other board also the atomic structure in class 12 physics. Okay, so go for that, and this will really help you. Okay, thank you.